Today we're talking about El Gordo, which is the fat one, which is a massive merging galaxy cluster in the distant universe. The reason I chose this was that recently there was an image released from James Webb Space Telescope predictably showing spectacular views of this massive galaxy cluster, in particular gravitational lensing. What we're seeing is a massive collection of galaxies all in the same region of sky. That's why they're a galaxy cluster. They're gravitationally bound to each other. But the incredible amount of mass that's there through their galaxies, as well as the dark matter that makes up most of the mass that we can't see here, produces these spectacular gravitationally lensed features. So these are optical illusions caused by the bending of light coming from distant galaxies, and that light's being distorted as it passes through the mass of that cluster, and we see these great big stretched out images of what are in reality quite normal, probably galaxies. So what we can see here are two examples of this in play. This thin one is called La Flaca, the flat one, and this beautiful thing is El Anzuelo, which is the fish hook, both names in Spanish. So I could talk about all of that, but actually I want to talk about why this cluster is important to cosmology in and of itself. So these are really recent observations, but this cluster was discovered over a decade ago. And even then, it was an object of interest. And the reason it was interesting is it had the potential to break cosmology. It sounds very dramatic, but when you think about the philosophy of science, we often talk about paradigm shifts, where we work with a theory until observations come that falsify it. And then we have to look for an alternative. And so for us right now, we have this sort of concordance cosmology where the lambda cold dark matter universe seems to explain what we see in the universe very well. Not everybody agrees with it, and there are problems with it, but it explains most observations in cosmology to a surprisingly good degree. But when you find an object like this, which is really big and formed really early in the universe, relatively speaking, it causes problems because it appeared at first glance like it might be too big, too early in the universe to be explained by our cosmological framework. And if that was the case, it had the potential to falsify that theory and make us re-examine what we were looking at in terms of explaining how the universe was formed.
Why can't you have something that big early in the universe?
So the way we think the structure in the universe forms is through a hierarchical process. So the early universe was very hot and smooth. It arose out of the Big Bang. As it expanded, things cooled down, but there were tiny little fluctuations in density. And once you run that forward for billions and billions of years, and you let gravity do its thing, those tiny little overdensities get magnified as they pull more material in. So the universe, the structure in the universe, we think is largely made up of smaller units of dark matter called halos merging together to form bigger and bigger things, and material collapsing in various directions and draining onto these nodes. So the problem is that takes time. You have to let gravity do its work. You have to let these overdensities become bigger and bigger and bigger. And to find something, when we look back in the distant universe, we're looking back in time because of the finite speed of light. It means we see something that early on in the universe. It only had 7 billion years or so to get as big as it was. That causes a problem for how we think all of this framework works. And what's special about El Gordo as well is that it's a merging cluster. As I just said, larger structures form from the mergers of smaller structures, but in this case, this is the merger of two really big things. This is a different view, which shows multiple views of the cluster all together. So you see the galaxies in the background. In pink, you see where the hot gas is, and this is revealed from the Chandra X-ray telescope. And this gas is sticky, so if there's a collision, well, the galaxies can go through each other and out the side. The gas tends to stick. And then the blue shows where we think the mass is. And this comes from gravitational lensing, a technique that we can use to actually reveal where most of the mass, mostly dark matter, we think, is in this structure. And so this is a beautiful example of a massive merging cluster. But again, something like that should be very rare. You shouldn't be able to find many of these, both because of the mass, because of the velocity with which they're colliding, and also because these things don't last very long. Observationally speaking, you only get to see them in this state for about 1 billion years or so. So, any random snapshot shouldn't find a lot of them. So it's a special object, it's a rare object, it's a massive object, and it formed really early on. This makes it worthy of further investigation. And so over the last decade, lots of people have looked at this and made independent measures, estimates of the mass using different techniques, all of them coming up with masses roughly within maybe a factor of 2, all of which showing that it's massive, but it's just on the borderline of being a problem. This is the original paper. So the title is The Atacama Cosmology Telescope, ACT-CL J0102-4915. That's its official name.
El Gordo is much catchier.
A massive merging cluster at redshift 0.87. I just want to take a moment here because we talk about papers, a lot, and they usually have just a name attached to them, and that's just anonymous scientists. But this person, Felipe Menanto, he's my friend. And well, at the time he was at Rutgers University in New Jersey, we had been office mates when we were PhD students. He was my academic big brother. He was the person on the desk over that I said, Felipe, why doesn't my code work? Felipe, what does this mean? Because, if these videos give us a chance to do anything, it's to underline the human side of science. And science doesn't get done without all of those people giving you support and answering your questions, even if they're not working directly with you. So it was lovely to give a shout out to Felipe for leading this work. And if I scroll down through the discovery paper, we get to a figure that illustrates what I was saying, which is this one here. This is trying to illustrate whether or not this is a problem. How rare and how unlikely this cluster is to form where it did in the cosmological model we think we live in. And so this goes out in time. So you can see at higher redshifts in the distant universe, hadn't had enough time to make a cluster. So these curves are all quite low. As time goes on, it gets more and more likely that we find one of these things. So this measures the mass that it could be. These 3 lines give an illustration of how likely it would be depending on how much of the sky you look at. If you look at the full sky, you would expect to find an object like this. But if you only look at a small patch of sky, like in a survey, you might not have the same chance. In fact, you'd have a much lower chance. And this single data point shows where in redshift and in mass our object is. And it's got an error bar. Error bars are really important, particularly for something like this. And you can see for the survey involved, this solid line here, it does sit right on the border. So it might be a problem, but it could be explained by normal formation scenarios. If it had been significantly above this solid line, it would have been a very big question. Like, why would we see that in such a small patch of sky? If it had been way above this dashed line, game would have been over. We shouldn't have seen it anywhere.
But it's pretty much on the line.
It is pretty much on the line, so that's why I want to talk about the importance of this error bar. Because before we throw out our entire scientific framework, we've got to have pretty solid evidence. And these measurements are hard. You're measuring the mass of something in the very distant universe. You can't pick it up and put it on a scale. You have to use indirect means to do this. All of those come with uncertainties. All of those come with assumptions about where the 2 clusters are on the plane of the sky, if they're colliding this way or that way, about how far out you measure them. They don't have an edge. You have to fit models, you have to extrapolate. Every single choice brings with it some measure of uncertainty. So that error bar is as important as the point that it goes around. And that error bar is large enough that it means we're not necessarily definitively breaking the cosmological model.
Professor Gray is based at the University of Nottingham. Check out the video description for more information about studying astronomy there. I'll also include links to some of my other channels, including Periodic Videos for chemistry and NUMBERPHILE for mathematics.
9, that is the first run of a 7 digits that go up. Obviously we're missing 1, 2 and 3. It would be nicer with them.